Hello everyone. So last time we spoke about the ideal transformer where there are no losses and you just had the voltages and currents being mapped from primary to the secondary through the turns ratio of the transformer. Today we're going to talk about the non-ideal transformer, which is closer to what we have in practice. So by the end of this session, you should be able to describe the main types of electrical losses that occur in transformers and draw these on an equivalent circuit. So just to remind you about the construction of the transformer, we have two windings and a core that links the primary to the secondary. And this acts again, if you remember, as a path for the magnetic flux to flow. So we could categorize the losses, based on these two types of components, the winding losses and the core losses. And when we come to winding losses, we're going to talk about resistance of the windings and the leakage inductance. And for the core losses, we're going to talk about hysteresis and eddy currents. So for the winding resistance, as we mentioned, was the I squared R losses, and these are due to the resistance of the conductor making up the coil. So remember, the conductor is made of copper, just like the other conductors you're accustomed to, and they have some resistivity. And if you could use your R is equal to rho L on A, and you could find what would be the DC resistance of the conductor, it actually increases with frequency, a phenomenon known as skin effect, which you should have covered in ECNG 1015, and that increases the resistance of the conductor. So that leads to some power losses. And then we also have leakage inductance, and this refers to the flux that does not link the primary to the secondary. So energy that is going into that flux does not make it across to the output of the transformer. Note, however, these are not power losses. Remember, inductances and capacitances, the average power dissipated is zero. So you have energy going into the field, but when the field collapses, the energy is released again. You do, however, get voltage drops across them, and the energy that goes into the field does not actually make it across. So we call it a loss because it is a loss in the sense of the power not making it to the other side, but it is not a loss in the truest sense because the power does not get dissipated as heat as it does with resistances. And these are represented as series losses in the equivalent circuit of the transformer. Coming to the core losses now, we have hysteresis, and this is the energy required to realign the magnetic domains with the applied magnetic field. If you remember your hysteresis curve, it will look something like that. And what happens is, as you magnetize the curve, it takes one path. But if you remove the magnetization, it will not immediately go back to zero. There is some inertia in the system, and you have to apply a force in the opposite direction to actually bring it back to the equilibrium position, or to the zero position. So this energy, which is represented by the area inside your hysteresis curve, is called the hysteresis energy. And of course, the higher the frequency, the higher the hysteresis energy losses. The eddy currents are another type of loss, and these are really I squared R losses that occur in the core. Remember, the transformer operates on the principle of electromagnetic induction, and the core is a conductor just like the secondary winding. So if the core experiences an alternating magnetic field, there will also be an EMF induced in the core, and then a current would flow in the core. So these currents, which we called eddy currents because they circulate, create I squared R losses in the core, and this is why we have core laminations and so on to reduce these effects. And again, you would have covered laminating cores in ECNG 1015. And lastly, we have the inductive impedance of the coil core arrangement. This is the main inductance, the inductance which you could look at as associated with the flux linking the primary to the secondary. And again, this is an inductance, so it is not in the strictest sense a power loss. It is a voltage drop. You'd have some current going into it, and you'd have some energy associated with the expansion of the fields, but when the field collapses, this energy is released. So in the strictest sense, it is not really a loss. Now, all these core losses are represented in a parallel circuit when we draw the equivalent circuit of the transformer. And if these types of losses do not sound familiar to you, then you should go back and look at your ECNG 1015 notes. So as we discussed, we have the ideal transformer here. We have the ideal transformer here. Sorry. And we have your core losses. We have the winding losses. So first the current comes into the winding. We create a magnetic field, then you get to the core. And then you have the secondary losses, which are also the heating of the winding and the leakage flux. So if we look at the transformer, we have a winding here and a winding on this side. So we have, as the current comes in, we have the resistance of the winding and the inductance of the field, the leakage inductance represented here. The remainder of the energy goes through the core, and you get your hysteresis and eddy current losses, your magnetization reactance, and those are the losses associated with the primary side. Then we have our ideal transformer, which represents the flux going from primary to secondary, and then on the secondary winding again we have the same resistance losses and leakage inductance as we did for the primary side. So this is really what the equivalent circuit looks like. Now we make one simplification, which is to shift the core branch from the inside here, and we shift it and we bring it here to the outside, to the terminals. So in essence, we would have this. So you might ask, well, how is that possible? How could we just move these components? So it is really a simplification, a mathematical simplification, and we could do it without much loss of accuracy. There is some loss of accuracy, but not much. And we could do it because these impedances are a lot larger than these. So if you want to see how that works, let's just imagine we have two resistances. Let's say this one is 1 ohm and this one is a lot larger, maybe 99 ohms to make it simple. And we have V1, and here I have V2. Then I could say V2 is equal to 99 on 100 V1. Now if I take the resistance and shift it to the other side, V1, V2, now I have no current flowing here, so this would be V2 is equal to V1. So this is 99% of V1. So you could see as the ratio of these resistances increases, as this resistance becomes very, very large, then the approximation or the effect of shifting the resistance from this side to this side becomes better. You get a smaller loss of accuracy, and that is essentially what we do when we move the circuit, when we move the branch from one side to the other. And as I said, this is really just a simplification to make the questions easier to work out. So our final equivalent circuit, we have a voltage applied to the primary, the input current, which we call I in, the core branch shifted to the outside, where we have the no load current, I no load, and that is comprised of I0, which is which contributes to the real power losses, and Im, the magnetization current. Then we have I1, which flows into the primary of the ideal transformer. Remember, this is the ideal transformer here. I1 flowing into the primary of the ideal transformer, and then we have the I2 going out of the secondary of the ideal transformer, and we have our winding losses on these sections here. So let's just go it over one more time. We have the core branch, the primary losses, winding losses, and this is the Joule heating and the leakage. We have the ideal transformer where we have our turns ratio N1 and N2. The secondary where we have the Joule heating and the leakage in those windings, and that is essentially our equivalent circuit with the losses included. So just to summarize, by now you should be able to describe the main types of electrical losses that could occur in transformers, and you should be able to draw the equivalent circuit for a transformer with losses. And here we're going to use the core branch on the outside, not on the inside of the transformer. If you don't remember the physical principles behind things like hysteresis and eddy currents, please revisit your ECNG 1015 notes. Next time, we look at referring parameters, and what I mean by this is bringing all the losses to one side of the transformer, and this is just a mathematical procedure we use to further simplify the circuit.